Okay, this next physics drill is going to be pretty interesting. We're going to be doing the equation recall drill. So we've got our list of topics here that we're working with in mechanics and electromagnetism. And then we're going to be given five random names, the equation names. And I'm going to try to remember them. The Euler-Lagrange equation is the first one. So that is a pretty simple one. It's just you take the sort of the derivative of the Lagrangian in terms of the velocity there, and then you can take the time derivative on this side, set that equal to the derivative of position. And the Newton-Lorentz force law, I know about the regular old force law like this, but what is the Lorentz force law? I mean, I know about this Lorentz force where we have QE plus QV cross B. But I don't know whether that's the Newton-Lorentz force law. Then we have Gauss's law, which is very easy. But I'm going to try to do a couple different versions of them because we have the regular old Gauss law we like to use, and then we have maybe the integral version of it, E dot dA range double integral is probably equal to triple integral. Uh, maybe it's the E dot dV. No. Maybe it's D dot dr. I can't remember exactly. It's hard to do this. Probably charge integral here? Hmm. Maybe it has to do with like this. Who even knows, to be honest? I'll just take a guess. Wild guess there. Um, but I also know that yeah, this could be written like this as well. P over epsilon naught. I think these are some different ways to write this Gauss's law. It's a pretty popular law. All right, we'll go and check our work a little later, and then we have Laplace's equation. That's like a given, always super easy to do this one. The multiple expansion formula. That one's really nice to remember, because remember we had the voltage, and usually if we do the Legendre expansion, we have to take we got one for epsilon naught here. You usually start with like A, L, R, L plus, and there's like a sum here, but whatever. B, R, the negative L plus 1, PL cosine. I'm just doing it for, like, I'm assuming that the azimuthal part is not here. And then this will probably go away because usually we take R going to infinity for the far field approximation. This is actually one of my favorite uh, equations that I learned during this course, so that's pretty cool. Now, let's get the answers. Answers. Oh, come on. No. Equations? Okay, what are the equations? Those five equations. Oh my God, the math. Dude, sometimes. Okay, yeah, so I was right about the Newton-Lorentz force thing. This was kind of correct. I got this one right, and technically this is correct. This is a simplification of the integral there. This multiple expansion is also correct, isn't it? No, it looks like I had something off on that. Interesting. So this is kind of a mistake, but I guess what it really is. So first of all, it's important to have the sum because we do have multipoles. So that means that we have a couple of them. Now, I know that this is definitely true. We have this sort of r to the negative l plus 1 over here. Or I guess it's a positive. It's on the bottom side, which why I don't like to put it down there. It makes me really confused. Where's the coefficient? Where's the b in the expansion? B coefficient. Yeah, the general multiple expansion, the exterior. We say that BL, this little thing. Oh, there's like a thing we have to do. So BL is equal to an integral. Whoa. Oh, wait, this is new actually. So we kind of put all the, we put everything into this coefficient. We put this into it, and then we even stick this into it, I guess. Um, maybe? It kind of looks like it, but I don't know. I'll have to like kind of clear that up later. But we did kind of get a little bit messed up on this one, so I guess we have to include like a cosine of y here. We need that charge density. We need that volume integral here. So that's what gets sort of put into this b term. So technically this is correct, but I forgot about like the integral for charge, I guess. This is like, yeah, this is a charge integral. So yeah, I guess so. I guess that's kind of makes sense. Okay, let's get 5 more problems. So next 5 names of equations. All right. So the Hamilton-Jacobi equation. Well, I don't know the Hamilton-Jacobi equation. I do know the Hamiltonian, kind of, maybe. What is it like? Something like this. Might be something like this. I mean, it's definitely just the kinetic energy plus the potential energy. But Jacobi, I don't know the Jacobian. I mean, I don't know the Hamilton-Jacobi equation. I do know the Jacobian. I guess we'll call it a J matrix if you want. As far as I remember, the Jacobian is a matrix that does something like d over dx, d over d. Um, I'm not really sure what we're doing the derivative of, but I know it's like a derivative matrix. I could guess. We could probably put fx here, fy here, and then it kind of does yeah, it probably does something like that. That's my guess. Y dx, and then I don't know what will be over here. This is probably completely wrong. And anyway, it's not even the correct thingy. So I don't know the Hamilton-Jacobi equations. We're gonna kind of give up on that one. We'll see how horrible this Jacobian matrix is. We'll check it out later. Let's get the Poisson equation. That one's easy. It's just that, although maybe I think it has a negative sign. The continuity equation? Oh God. Okay. I know that there's like a J in it. That's a current. Um, I think there's like a charge in it somewhere. It might be something like this. I don't know. Kind of reminds me of something. I don't know. I don't know the continuity equation that well. And then the Maxwell Ampere law. Didn't we do this the other day? The Maxwell Ampere. That one's a hard one. Um, I think it has epsilon naught e in it, and I think we're taking a time derivative of it. I think we have the mu naught e in it. No, I think again the J appears here. Oh, I think that equals 0. It's probably wrong. Okay, okay, what's the 5 maths equation here? What the heck is that? ds over dt plus hqi. This is like a vector of some sort. We have qi ds over dqi, and then t is equals 0. Well, that's cool, but I don't know if we're ever going to use that. So I don't know how that's gonna help. Wait, did I forget the wave equation? Wow, I did forget the wave equation. All right, well, that sucks. What is the wave equation? It's kind of like, do we use y? D over dt. Oh, the wave equation is just this. It's like mx plus um, kx equals 0, I think. No, that's just simple harmonic motion. Hmm. Second derivative in terms of space for something we usually do like the E field or something, and that's supposed to be equal to 1 over mu naught epsilon naught, and the second derivative in terms of time for the same field. Yeah, this is the wave equation in a more familiar form. Okay, Poisson's equation right here, continuity equation. Well, I had the right symbols. It was close. Just clean it up a little bit. So it's more like the time derivative of the density, and then the gradient or the div of this field, and this is continuity. I think this is the div of the charge, like the current. So we have density and current. I'm sure this is charge density. Charge density, and then the divergence of the current is the continuity equation. So this is one that I should probably put in my notes because, it's just fun to have it, I guess. Very popular. This one, I was close. I just needed the mu naught right here. And it's not equal to zero. It's equal to the B cross, yeah, the cross of B. And the curl of B is equal to this. And we just need mu naught right here. Boom. All right, so that was kind of fun. I guess we could maybe try one last batch. Oh no, that was 10. Took a while. I don't know how much time this has been. We'll probably call it here. Thank you much for watching.